They say a generator is connected to the wheel or hub of a bicycle and can be used to power lights or small electronic devices. A typical bicycle generator supplies 6 volts when the wheels rotate at 20 radians per second. If the generator magnetic field has a magnitude B equal to 0.600 Tesla with 100 loops, 100 turns, find the loop area A of this generator, right? Second question, find the time interval between the maximum electromotive force of 6 volts and the minimum electromotive force of 6 volts. So how we can solve this? So what we know? Well, the information that is given here is that the generator supplies 6 volts. So the electromotive force will be 6 volts. And we also know, that the wheels rotate with a frequency of rotation of 20 radians per second. 20.0, let's say 20.0 radians per second. Use the same number of significant figures. 20.0 radians per second. What else we know? We know that there is a magnetic field of 0.600 Tesla. We know we have 100 loops or 100 terms. And we want to find the area. So the unknown here is the area. Now, what we know? We know that this maximum magnetic field, this maximum electromotive force, you remember the equation, right? Of electromotive force, we said that electromotive force is MVA omega sine of omega t. So we said the electromotive force is equal to the number of loops times the intensity of the field times the area times the frequency of the rotation times the sine of the frequency times the time. Right? Now, these 6 volts is the maximum value of electromotive force. And that maximum value is when the sine of omega t is 1. So when sine of omega t is 1, we have the maximum value. That will be these 6 volts. So we can say now that this E would be number of loops, or number of terms times magnetic field times area times frequency of rotation. I can solve for the area, so I can say that E divided by the number of terms times the intensity of the magnetic field times the frequency of rotation would be equal to the area. And the intensity of the magnetic field times the frequency of rotation would be equal to the area. So the area would be 6 volts divided by, we have 100 terms times 0.600 Teslas times 20 radians per second. Now, when you find the area, now you can find that the area would be 0.005 meters squared, which is the same that 5.00 times 10 to a negative 3 meters squared. So that is the area, of the loops in your generator, the bicycle generator. Now, they say find the tiny interval between the maximum electromotive force of 6 volts and the minimum electromotive force of minus 6 volts. So remember that this generator is going to generate an alternate current. And then, what happens here is that in this graph of electromotive force versus time, do we have a maximum electromotive force here equal to positive 6 volts, and you will have any minimum electromotive force here that is negative 6 volts. And then, of course, you have the values oscillating between minus 6 and 6 volts. Now, what they ask you here is find the time interval between the maximum electromotive force of 6 volts and the minimum electromotive force of minus 6 volts. So basically, they want to find how long it takes, from this maximum to this minimum electromotive force. So they want to find this time interval from the maximum 6 volts of electromotive force to the minimum 6 volts of electromotive force. They want to find that time interval. Well, in the equation of electromotive force, the time is argument of the sign. So the time is part of the argument of the sine function. So we have to find, in this case, the isolated sign and use the sign inverse to be able to calculate, this value. So what I'm doing, I will calculate the value that takes, to have a change in just 6 volts. So this is completely symmetric. So this function is symmetric. So if I find the time from 6 to 0, that time from 6 to 0 is the same as the time from 0 to minus 6 volts. So the only thing I have to do is to calculate the time from 6 to 0 and multiply times 2, for example. So I can say that I know that if the electromotive force is 6 volts, and I know the number of terms, that is 100, and I know the magnetic field, that is 0.600 Tesla, and I know the area because I found it, that is 5.00 times 10 to the negative 3 meters squared, and I know the frequency of the rotation, that I know is 20 radians per second. I can solve for the sine of omega t. So I say, solving for sine of omega t, electromotive force, sorry, let me change the color of the marker, divided by number of terms times magnetic field times the area of the loop times the frequency of the rotation is equal to the sine of omega t. Now, what is the problem? My problem is that I have to find then, the inverse function. So omega t would be the sine inverse of E over, so electromotive force over number of loops, number of terms, times magnetic field times area times omega. So you can calculate this now. So omega t is the sine inverse of substituting, you say 6 volts over the number of loops, which is 100, the number of terms, which is 100, times B, which is 0.600 Tesla, times the area that we found, that is 5.00 times 10 to a negative 3 meters squared, times the frequency that we know there is 20 radians per second. We get that omega t is the sine inverse of, and then we get 1 here, sine inverse of 1. Well, the sine inverse of 1, the sine inverse of 1 is 1.57. The sine inverse of 1 is 1.57. 1.57 radians. So omega t is equals to 1.57 radians. Now, solving for t would be 1.57 radians over omega, which is 1.57 radians over 20 radians per second. And then when you calculate t, it would be 0.0785 seconds. Now, what t I found? The t that I found is this, from 6 volts to 0. So if I want to find the time interval from 6 volts to minus 6 volts, I have to multiply this value of t that I found times 2, which is then equal to 0.157 seconds, is 2 times 0.0785 seconds, which is 0.157 seconds. And now this is the time that goes, or that took, to go from 6 volt positive to minus 6 volts here. And it's using the equation that I gave you, at the beginning today, to calculate the electromotive force in a generator. So this is, the solution of this exercise. In this, they say the current in a coil drops from 3.5 amperes to 2.0 amperes in 0.50 seconds. If the average electromotive force induced in the coil is 12 millivolts, what is the self-inductance of the coil? So let's analyze, what are the values they give us here. So what are the knowns and unknowns? So we have an initial current. There is 3.5 amperes. And you have a final current of 2.0 amperes. So if you find the variation of current, this variation of current, delta I, there is I final minus I initial, is 2 amperes minus 3.5 amperes is minus 1.5 amperes, right? So there is a variation of current of minus 1.5 ampere, and this variation of current is occurring in a variation of time of 0.50 seconds, right? So this is delta T, and then this one is the initial current, and this one is the final current. Now, what do they say? They say that the average electromotive force induced in the coil is 12 millivolts. So the electromotive force average is 12 millivolts, which is 12 times 10 to the negative 3 volts. Okay? Now, we know that the equation that relates the inductance and the electromotive force and the variation of current and the variation of time is that the electromotive force is equals to minus the inductance times delta I over delta T. What I have to do, I have to solve for this inductance. So I can just multiply by negative the reciprocal of delta I over delta T, which is delta T over delta I. So I can say that negative E, negative electromotive force times delta T over delta I is equal to the inductance. So the inductance will be negative 12 times 10 to a negative 3 volts times delta T. There is 0.50 seconds divided by, and then delta I, which is negative 1.5 amperes. And now when you calculate this, we get that this is equal to 4.0 times 10 to a negative 3 Henry, or which is the same that 4.0 millihenry. 4.0 millihenry. So the inductance, in this case, the self-inductance of the coil is 4.0 millihenries. Now, let's solve another exercise also involving, the inductance. And in this case, also the variation of current. Look at my next exercise. They say a solenoid of radius 2.5 centimeters have 400 turns and a length of 20 centimeters. Find its inductance and the rate at which current must change through it to produce an electromotive force of 75 millivolts. So basically, they say that we have a solenoid right? And then the length of the solenoid is 20 centimeters. 20 centimeters is the same as 0.20 meters, right? Now, what else we know? We have 400 turns. And the solenoid have a radius. And the solenoid have a radius of 2.5 centimeters. Now remember that 2.5 centimeters is 0.025 meters. So that radius is also 0.025 meters. Now, if I want to find the inductance of this solenoid, I know that the inductance would be mu sub 0 times the square of the number of turns times the area over the length. I don't know the area yet, so I can calculate the area, of the loop, and the area of the loop, which is pi r squared, is going to be pi times 0.025 meters squared. So the area will be, in this case, 1.96 times 10 to the negative 3 meters squared. So if now I know the area, I can just calculate the inductance. So we say that L is equals mu sub 0 4 pi times 10 to the negative 7 Tesla meters per ampere times the square of the number of terms, so 400 squared, times the area, 1.96 times 10 to the negative 3 meters squared, divided by the length, which is 0.20 meters. So now when we calculate this inductance, we find that the inductance is going to be equal to 1.97 times 10 to the negative 3 henries, which is 1.97 millihenries. 1.97 millihenries. But this is just only the first question. The second question says that we must find the rate at which current must change through it to produce an electromotive force of 75 millivolts. So when they ask you about the rate at which current must change, they ask you to calculate delta I over delta T. This is the rate of change of the current. Delta I over delta T is the rate of change of the current. Now, if we have to calculate delta I over delta T, remember that also we can calculate the inductance as negative there is a, let me go first to the original formula. We can calculate the electromotive force like negative the inductance times delta I over delta T. So this is the formula that I can use to calculate the electromotive force. Now, the negative sign, remember, that represents that the current will oppose to the change, right? And the induced current will oppose to the change, right? So I can get rid of the negative sign, because at the end, what this negative sign is doing is representing that the current that we generate opposed to the change. So I need to solve for delta I over delta T, so I will divide the electromotive force by the inductance, and this is equal to delta I over delta T. So we can say that delta I over delta T will be equal to the electromotive force, 75 millivolts, which is 75 times 10 to a negative 3 volts, divided by the inductance that we found that is 1.97 times 10 to a negative 3 henries. So the rate of change of the current with the time is, when we calculate 37.5 amperes per second. 37.5 amperes per second, which is approximately, to rewrite this in with two significant figures, 38 amperes per second. So to produce this electromotive force of 75 millivolts, the rate of change of the current with respect to the time needs to be equal to 38 amperes per second approximately. But this was another exercise, about the inductance. I have here now one more exercise that is about an RL circuit. This one is about an RL circuit, because they say, in this case, right, that the battery terminal voltage is 39 volts and the current I reaches half its maximum value of 2 ampere at 0.100 seconds after the switch is closed. So they are asking to calculate the time constant. They are asking to calculate, in this case, the electromotive force across the inductor at the time constant equal to 0.100 seconds. And what is the electromotive force across the inductor in the instant after the switch is closed at time equal 0 seconds. So what is the circuit that we have in this case? The circuit we have in this case is a resistor inductor circuit. So we have here the battery, some electromotive force. Then here I have a switch. I have one inductor. And I have one resistor. This is my circuit in this case. So this is an RL circuit. It's a circuit that contains a resistor and an inductor. Resistor and inductor. So how can we calculate the time constant? Well, what we know here really is the equation that describes the behavior of the current in this kind of circuit. And the equation that describes the behavior of the current in this circuit is that the current I, as a function of the time, is that the current I, as a function of the time, is equal to the electromotive force of the battery divided by the resistance of the resistor times 1 minus the natural base e to the power of negative t over tau. Now, what is this E over R? E over R is the maximum current. So E over R is the maximum current. And that maximum current is 2 amperes. Now, there is something here that is very important. Anita, they say here that the current I reaches half of its maximum value of 2 ampere at 0.100 seconds. So at 0.100 seconds, you know, the current reached the half of its maximum value. So when t is 0.100 seconds, the current is 1.00 amperes. So I can rewrite now this as I of t is equals I maximum times 1 minus e to the power of negative t over tau. Now, the I maximum, we know there is 2 amperes. And as when t is 0.100 seconds, I is 1 ampere, I can now substitute this I by 1 ampere when now t is 0.100 seconds. So e to the power of negative 0.100 seconds divided by tau. Now, this is an exponential equation where the noun we want to find is in the exponent. So this is the kind of equation that we have to solve using logarithms. So what are we doing? We're going to divide 1 ampere by 2 amperes. So we get that 0.5 is equal to 1 minus e to the power of negative 0.100 seconds over tau. I will be subtracting 1. So when I subtract 1 from both sides, I will get that 0.5 minus 1 is equals negative e to the power of negative 0.100 seconds over tau. This is negative 0.5 equals to negative e to the power of negative 0.100 seconds over tau. Negative in both sides, multiplying both sides by negative 1, we get 0.5 is equals e to the power of negative 0.100 seconds over tau. I now apply natural logarithm. Natural logarithm of 0.5 is equal to the natural logarithm of e to the power of negative 0.100 seconds over tau. So using property of logarithms, natural logarithm of 0.5 is equal to negative 0.100 seconds over tau times the natural logarithm of e, which is 1. So solving for tau, you can say that tau times the natural logarithm of 0.5 is equal to negative 0.100 seconds. So you can say that tau is equals to negative 0.100 seconds over the natural logarithm of 0.5. So when you calculate tau, the time constant, you get that the time constant is 0.144 seconds. This is the time constant of this circuit. This is the time constant of this circuit. So time constant is 0.144 seconds. Now, the next they want to know is what is the electromotive force across the inductor at t equals 0.100 seconds. At t equals 0.100 seconds. Well, the problem here is that now we will have a drop of voltage across the inductor, and you will have a drop of voltage across the resistor. And the total, by law of conservation of energy, exactly as we did with the Kirchhoff rules, the total energy, when you go around, the total voltage, the sum of all the voltage, of all the local voltage, of all the variation of voltage, across your circuit needs to be equal to 0 to have conservation of energy. So you can say that the electromotive force plus the drop of voltage across the resistor plus the drop of voltage across the inductor needs to be equal to 0. Now, I want to find the drop of voltage across the inductor. So I will solve for the drop of voltage across the inductor. So the variation of voltage across the inductor would be negative the electromotive force minus the variation of voltage across the resistor. Right? Right? Now, what happens here? The variation of voltage across the resistor will be the current that we have at 1 second times the resistance of the resistor. That would be the variation of voltage across the resistor. So we can say that the variation of voltage of the inductor would be negative the electromotive force of the battery minus, and then here we have the voltage across the resistor, which is negative I times R. Sorry, this is variation of voltage across the inductor. So we can now say that the variation of voltage across the inductor is negative 9.0 volts plus that the current was 1 ampere and then we don't know yet what is the resistance of the resistor. So as R is unknown, we know that R, the current maximum, is the electromotive force over the resistor. So the resistor has a resistance that is the electromotive force of the battery divided by the current maximum. That current maximum was 2 amperes. So you can say that the resistance of the resistor is the 9 volts of the battery divided by the 2 amperes, which is going to be equal to 4.5 ohms. So now that you know this resistance of the resistor that was unknown here, you can substitute and say that the maximum current is equal to the maximum current of the variation of voltage across the inductor because we're going to substitute the resistance in the variation of voltage across the inductor. So the variation of voltage across the inductor would be minus 9.0 volts plus 1 ampere, times 4.5 ohms. So delta V across the inductor would be negative 9.0 volts plus 4.5 ohms, which is negative 4.5 ohms. This would be negative 4.5 ohms. We just rewrite this. So the variation of voltage across the inductor would be negative 4.5 volts. Now we need to calculate something else. That is, what is the electromotive force across the inductor in the instant after the switch is closed at the time 0. At time 0. Just to analyze what happened in that case. What do you have? Let me erase one part over here. Let me erase just this part. So what about this part? You know that the electromotive force, right, is equal to, in this case, the A maximum times, in this case, 1 minus e to the power of negative t over tau. Now, what happens? They say at time c, when tau is equal to 0. So when tau is equal to 0, look at what happened here. 1 minus e to the power of negative t over c, or the number that approaches to 0. Now, but this exponent is negative. So we have 1 minus 1 over e t over a number that approaches to 0. E to the power of t over 0, this number approaches to infinity. And 1 over a number that approaches to infinity approaches to 0. So this would be E maximus times 1 minus 0, because this whole expression approaches to 0 when the denominator approaches to infinity. So this would be equals to the E maximum. There is just the electromotive force of the battery. So this is just 9 volts. So what is the electromotive force across the inductor in the instant after the switch is closed at time 0 is equal to 9 volts.